Hello, my name is Lisa Fred Miles, and I'm from Southern West Virginia Community and Technical College. And today we're going to be looking at probability. Probability, you may not realize, but you estimate probabilities every day in your life. Anytime you informally observe the likelihood of an event, you're using probability. For instance, did you think about the chances it was going to snow today? Or did you think about the chances it was going to rain today? Or what are your chances for getting a certain grade on a test? These are all probabilities, but they are informal. Now, there are two types of probabilities. Actually, there's more than two, but we're going to look at two: theoretical probability and empirical probability. When you think of empirical probability, think of an experiment. I have to do some sort of trial or experiment and get actual data, and then I use that data to calculate probabilities. And I calculate it by taking the number of times an event occurs over or divided by the total number of observed occurrences. Theoretical probability is kind of like in theory. It's the likelihood an event will occur based on what I know to be the possible outcomes. It is calculated by determining the number of ways an event can occur divided by the total number of possible outcomes. So in other words, the number of favorable outcomes divided by the total number of outcomes. These two formulas probably mean nothing to you right now, but let me demonstrate both, and I think these definitions will make a lot more sense. First, I'm going to look at theoretical probability. Here you notice there's a spinner, and on this spinner right here, there are 7 different spaces that the spinner can land on. That is the total possible number of outcomes. This spinner right here can land on one of these 7 different spaces. But if I wanted to find out, for instance, the probability of red, written this way, P and then in parentheses red. If I wanted to figure out the probability of a spinner landing on red, I would say, well, there's 2 red spaces out of the total number, which is 7. So that is the favorable number, red, so there's 2 of them, divided by the total outcomes, 7. So it would look like this, 2 over 7. Notice that this number is smaller than 1. A probability will never be more than 1. It can equal 1, but it will never be more than 1. Likewise, it will never be less than 0. You can't have a negative probability that something's going to happen, but you can have 0 probability. For instance, if I said, what's the probability that tomorrow it's going to be 110 degrees outside? Well, you would say there's 0 probability of that. So using the same idea, what's the probability of getting blue? Now mine, blue space looks a little purple here, but let's just say it's blue. The probability the spinner is going to land on blue, where there's 1 blue out of 7, so the probability of blue is 1 out of 7. Probability of yellow, see if you can get it before I show you. Did you get it right? 2 out of 7. The amount of favorable outcomes, which is 2 yellows, total number of outcomes, 7. What about the probability of green? See if you can figure it out before I show you. Again, 2 out of 7, because there's 2 greens, and right now green's the favorable out of 7. This is theoretical probability. We didn't ever spin this to find out our probabilities. We simply used the diagram itself to figure out our probabilities. Now we're going to do empirical probability, which is, remember, it's also sometimes called experimental. So that kind of lets you know you're doing an experiment. So what we're actually going to do is spin the spinner. And we're going to spin it 10 times. So, and keep track of what we get in this handy dandy little chart here. Okay, so let me get my marker. spin it. Spin it, and I get a yellow. So I'm going to put a mark under yellow. We got yellow one time. Now let me spin it again. This time I get a green. So I'm going to put a mark under green. I'm going to do this for 10 times. I've done 2 so far. Third time I get red. Next I'm going to get another red. So tally mark under red. See if we get it again. We get red again. That's 5 times. I got 5 more times to do it. Another red. Yellow. That's 7 times, so 3 more. Yellow again. I might not get it yet. I might not get blue at all. There we go. I got a blue. And I think they got one more time. It's right on the line. I'm going to call that a green. Looks a little more to the green for me. Okay, so I've collected my data and I've put it in this chart down here. This is my experimental probability because I actually collected the data using real life happenings. So the probability of getting a red, well, I only spun the spinner 10 times. So the total possible number of outcomes is going to be 10. That's going to be on all of my bottoms. But the number of times, favorable times that it actually ended up red was 4. So the top number is going to be 4. So it's 4 out of 10 is my probability. Now, you can reduce 4 out of 10 to be 2/5. But probability is one of the few times that you do not have to reduce your fraction. It's not wrong to say 2/5, but you could just as easily say 4/10. Now, the probability of getting blue would be 1 time we got a blue out of 10. So again, our bottom number is 10, but our numerator is 1. 1 out of 10 times it landed on blue. Yellow, again, we did 10 trials, so 10 is our bottom number. But 3 of those times it landed on yellow. So the probability of yellow is 3/10. Again, notice all of these numbers are less than 1 but greater than 0. A probability can equal 0 and it can equal 1, but it can't be greater than 1 and it can't be less than 0. Probability of green, well, green occurred 2 times, so 2 out of 10. Which we could reduce to 1/5, but we don't have to. Let me just go ahead and write that there. Now, notice if I were to take all of these probabilities and add them up, that is the 2/5, 1/10, 3/10, and 1/5, or if I just wanted to stay with the 4/10 plus 1/10 plus 3/10 plus 2/10, I could add, since they all have a common denominator, 10, I take the 4 plus 1 plus 3 plus 2, and I get 10, or 10/10. Probabilities, 10/10 is the same as 1. Probabilities will always add up 2, 1. If you take all the different possible things like yellow, green, red, and blue, and take all the different probabilities and you add them up, you will always get 1. So that's like a way to check yourself and make sure you did it right. This is empirical probability, and the one we did before where we didn't do an experiment, where we just looked at the spinner, was called theoretical probability. Now, in the beginning, I gave you 2 formulas for probability, but really, there's just one. Both of them are just the number of times you want it to happen, or it did happen if you did an experiment, divided by the total number of times you're looking at, or the total number of possibilities. So don't think of this as 2 different formulas, always thinking of it as the favorable amount divided by the possible amount. Now, this leads us to an interesting thing. Why are empirical and theoretical, why do we get different values? Well, let's go back and look and see that we got different values. See, for instance, the probability of red here was 2/5, and the probability of red was 2/7. See, we're getting different amounts. Well, you will not get different amounts eventually. What the law of large numbers says is that eventually, if you do the experiment enough times, over and over and over and over, say 25 to 100 times, the empirical probability and the theoretical will be the same. So the moral, I guess, the moral of the story of the law of large numbers is you can't just do 10 trials like we just did. We just did our experiment 10 times. We don't want to do that. We want to do it a lot more times than that, say 100 times, before our probabilities start to look like the empirical value. Here is a probability from the game show Wheel of Fortune. Okay, so Wheel of Fortune has this wheel, and in the wheel you can count how many different opportunities that we have. We've got bankruptcy, 135, 180, and so on. That's 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, and 12. So there's 24 total different things that the spinner can, or this little peg here can land on. 24. So what's the probability that it will land on bankrupt? See how we write P of bankrupt? Well, since there's 2 favorable events, 2 possible times it can land on bankruptcy, and 24 total, then we say the probability is 2 over 24 or 1 over 12. And again, with probabilities, you do not have to reduce your fraction like you do on other types of problems. Now, would that, what we just did up here, the probability of bankruptcy, would that be an example of theoretical or empirical probability? Think about that. Would it be theoretical or empirical? And the answer is, it is an example of empirical, because we didn't actually do an experiment. If we had actually spun the spinner, say 24 times, then we can get empirical. This was theoretical. Oh, I'm sorry. This was an example of theoretical probability. We can make it empirical by actually spinning the spinner. All right, let's say we have a little bit more complicated of a problem. Let's say that we have 2 spinners. We have one that has numbers 1, 2, 3, and 3. And then we have another one that has colors, red, purple, yellow, another red, and green. Well, it's really hard to say what is the probability of, say, it landing on a red and a 3, or landing on a red or a 3. Now, remember what and or mean in your definitions from before. So it's really a little bit difficult. Just by looking at that, theoretically, it's a little bit hard to tell. But we can still find theoretical probabilities by making what is called a tree diagram. So the first thing we do on a tree diagram is we list all the different choices for one of the spinners. I did the color one. So red, and I put a little dot by it, and notice a dot down here just so I can keep track of which red. And then there's this other red here. There's also a green, a purple, and a yellow. These are all the different color options. Now I could have put, instead of color options here, I could have put my number options. It does not matter which one you put first. But now if it lands on red, the first spinner, or this spinner down here, lands on this red with a dot, the top spinner could land on a 1, or it could land on a 2, or it could land on a 3, or it could land on a 3. There's no guarantee which one, just because it lands on red down here, it still could land on any one of these. So my options are that it could land on red and a 1, red and a 2, red and a 3, or red and a 3. There are different options for red. The same is true with any color. Any color the bottom spinner lands on, the top spinner could land on any one of these 4 spaces. So all of these have the same options. Second one, red, 1, 2, 3, or 3. Green, 1, 2, 3, or 3. All of them have the same second spinner's options. So now here are our total probabilities. If I land on red with a dot, then I could have 1. Or I could land on red and 2. Or I could land on red and 3. Or I could land on red and 3. So we create what's called a sample space over here. Red with a 1, red with a 2, red with a 3, red with a 3. These are all the different combinations that the 2 spinners can land on. Second set of combinations are the same because, again, I'm looking at my red spinner. Third set of combinations are green. So it could land on green with a 1. One spinner lands on green, the other a 1. One spinner lands on green, the other a 2. Green 3, green 3. And the same with all of them. Purple 1, purple 2, purple 3, purple 3, and yellow 1, 2, 3, and 3. So these are all the different possibilities, all the possible outcomes. And if you notice, there are not just, say, 7 or 9, because I have 9 different spaces. There's actually 4 plus 4 plus 4 plus 4 plus 4. There's 20 of them, which happens to be the number of possible outcomes for the first spinner times the number of possible outcomes for the second. 5 possible here times 4 is 20. That's how many different options I have. So what's the probability that it will be a red and a 3? Well, remember, and means it has to be red and it has to be 3. Well, if we look, that only happens 1 time, 2 times, 3 times, 4 times. Out of all those times, 4 times it could land, there are 4 favorable times it could land on a red and a 3, which means my probability is 4 out of 20. Four out of 20. And of course, again, we could reduce that to 1 out of 5, but we don't need to. Okay, now let's do the next one. Probability of a red or a 3. Very, very subtle difference there. Just the word or instead of the word and. So that means it could land on a red, or it could land on a 3, or it could land on both, remember. So here it lands on a red, so that counts. It lands on red, so that counts. Here it lands on red and a 3, but it only counts one time, remember, because or includes both happening. Here's a red and a 3. Here's a red and a 1, so that's at least a red. Red and a 3, so that's at least a red. Red and a 3, so that's at least a red. Red and a 2, so that's at least a red. And then down here, I have at least a 3 happening, because remember it's or, which means either one can happen. And so for each of these colors, it lands on a 3 twice in the combination. So red or 3 happens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times. 14 out of 20 times it lands on a red or a 3.
It really does.
There we go, 14 out of 20. Okay, now let's look at the next one. The possibility of just a red. Well, erase all these that don't have red. How many times can it land on a red? How many different times out of all of these combinations? 8. 8 times it has the possibility of landing on a red out of 20. So you may have wanted to say 2 out of 7, but you got to remember, because we're doing both things out at the same time, there's actually 20 possibilities now instead of 7. So 8 out of 20 times it lands on a red. What about not a red? So we're going to erase all the reds. We don't want red. So how many times does it not land on red? We don't care about the number. We're only looking at not red. Well, green is not red. So actually all of these greens, all 4 of them. Purple's not red, so all of these purples. Yellow's not red, so all of these yellows. So that's 4 plus 4 plus 4, that is 12, 12 possibilities, favorable outcomes out of our number is 20. So that's 12 out of 20. 12 out of 20. Let's do a couple more. Probability of yellow and 2. So the bottom ones are yellows. So I'll keep them. So we got 4 possible times it could be yellow. And then we also, but it cannot just be yellow, it has to be yellow and 2. So out of those possibilities, the only ones we want is this one. We don't want the other ones because and means both things have to happen. So that is 1 time that happens out of 20, or 1 over 20, 1 out of 20. We changed that word and to or, and we've changed our problem. Now we have 8 out of 20 because we can count all 4 of the yellows when we have an or problem, and we can also count all of our 2's. So that one might be wrong. Nope, that's right. So we've got all of these 2's also count. So we've got 1, 2, 3, 4, 5, 6, 7, 8 times. It is either, let me redo that because I circled the 2's. Misread my question. It's yellow or a 1. So 8 times still, because see, there's 1, that's a 1. 2, that's a 1. 3, that's a 1. 4, that's a 1. And then these 4 down here that are yellows. And this one that's yellow and a 1, we do not count it twice. This is just one event. So total we have 8 out of 20. And now the probability of yellow and purple, and means both have to happen. Well, if you notice, that never happens. We never get yellow and purple. So that's an example of a 0 probability. 0 out of 20, which is 0. Okay, so that's how we can use what's called a tree diagram. We set up all our possibilities for spinner number 1 or event number 1, all of our possibilities for the second event, and then we create this sample space by following our chart. So we've got red follows 1, red 1 is one possibility, red following 2 is another, red following 3, red following 3. We set up our sample space with all the different possibilities. We count up how many total outcomes there are. That's our bottom number on all of these. And then the number of favorable is still our top. Notice that now the problem was more complicated. We did two things at once, but the formula stays the same. Now, I want to point this out because when you're doing probabilities, you will read in the chapters and in different books that there are all these different formulas for probability. But in reality, there is always one formula. The number of favorable outcomes over the total number of possible outcomes. The formulas are just because they found these other little tricks that work. But if you always think of what are the total number of favorable outcomes over the total number of outcomes, that will always work for probability. The problem is trying to figure out the number of possible outcomes. And that's where something like a tree diagram really starts to help. It helps you organize how many times something can happen. Now, what we just did was theoretical. Let's do it experimentally. So, to do it experimentally, I have to set it up so that my choice one of my choices is along the side here, and one of my choices is along the top. It's very similar in idea to that two-way table we did. As a matter of fact, this is a two-way table. It just has more options. The one you did had 2 options here and 2 options here. And we just have more options. So we're going to spin each of these. Okay, so I spin both of them. Let's see where it turns out. I get a purple 1. So under purple 1, I'm going to put a little tally mark. Let's do both of them again. We're going to do this 20 times. I'm going to call this, I'm not going to include any lines, by the way. I'm going to call it a 2. So it's a red 2. A red 2. Now, I'm saying this first one right here is my red with a little dot. The second one's without, because I want to keep this straight. Even though in the end it's not going to make that much of a difference. All right, we're going to spin it again. That's 2 times. Red 2 again, only this was the same red, so that's the same thing, red 2. A little tally mark there. And again, a red 3. Yellow 1. Okay. A green 1. I call that a yellow 1. I'm just going with which one it looks closer to being on. A red 3. This is the stop red. Another red 3. It really doesn't matter which red or which 3 because it's not gonna. I'm gonna have to add them up anyhow for my probabilities. a purple 1, I think that's 10 times, so we got about 10 more to go. A red 3, a red 3, a yellow 3, a red 2, purple 1, red 2, yellow 2, I think that's 17, red 3, we're getting a lot of red 3s, yellow 3, okay, so we got 15, 16, 17, 18, 19, 20, 21, 25, 26, 27, 28, 29. I did too many. That's okay. Let's just do one more. So that is a red 3 again, which makes a line here. Okay, so that's 5, 10, 15, 20. Okay, that's good. 5, 10, 5, 10, 15, 20. Okay, I did the right amount. Good. Okay, so the probability of red and 3, so it has to be red and 3. That is, here's the 3's. These two columns are 3's. And these two columns are reds. So remember, and is where it's both. So it would be 5, 6, 7. 7 out of the 20 times we did it. So that would be 7 out of 20. 7 out of 20. Okay, the probability of red, well, that's both of these reds. How many times did it land on red? 5 plus 5 is 10. So I'll add up all of these and we get 10. So it landed on red 10 times out of 20. The probability of, oh, that's 10, sorry, it goes down here. Probability of red is 10 out of 20. Right, like that. The probability of red or a 3 means it could be one of the, something in these columns, 3, or it could be something in this column, red. And where they overlap here, these 7, we're not going to count them twice. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 total are red or 3. Probability of not red. Let me erase my little lines here. Without erasing any of my purple tally marks. Okay. So the probability of not red, that's all of these that are not red. It could be purple, yellow, or green. All of these are not red. And that looks like 9. 5, 6, 7, 8, 9. So that is 9 out of 20 were not red. I don't want to use that color. 9. 9 out of 20. Okay, now the probability yellow and 2. So again, it's got to be both. So we've got yellow and we've got 2. So we've got 4, 5, 6, 7, 8. Now notice I did not count this one twice. It does not get counted twice. So that's 8. Oh, that's 8 for yellow or 1, because it could be either or. So that's for the or, that's 8 out of 20. But when I say and, it can only be yellow and 2. It has to be both, which is just this one in the intersection of the two, the column and the row intersect at 1. So the and is the intersection. The or is all of them, the union. And again, probably yellow and purple, as you can see, that never happens, that both occur, so it's still 0. Again, our theoretical probabilities and our experimental probabilities are not always the exact same thing, because we have to do many, many, many of these experiments before they're the same thing. Now here's a game you can play with your friends. It's called the multiplication game. And the rules are you roll the dice. Now you have 2 dice. You roll them. If the product is odd, player A gets the points. And if the product is even, then player B gets the points. And product means to multiply them together. The player with the most points after 36 rolls wins the game. Well, the problem with this game, and you don't tell your friend, you just kind of like say, hey, I'm going to bet you some money. You get odds, and I'll get evens. Well, off the bat, you're probably thinking, well, there's probably the same probability or the same chance of getting odd as even. But let's look at this theoretically. Okay, so here is our table we're going to use. We have 1 dice, which we can get a 1 through a 6. The second dice, we can get a 1 to a 6. So we're setting up our table similar to the one we just did. So this represents 1 die we roll, 1, 2, 3, 4, 5, or 6. Second die we roll, 1, 2, 3, 4, 5, or 6. Now let's look at all the different products here. Okay, so 1 times 1, our product is a 1. 1 times 2, our product is a 2. 3 times 1, our product is a 3. And so on and so forth. All of these on the first row, when we multiply them times 1, it's not going to change the number on the second dice. No. Second time, say we roll a 2 and a 1, we again get 2. Say we roll a 2 and a 2, our product becomes a 4. A 2 and a 3, our product is a 6. A 2 and a 4, our product is an 8. A 2 and a 5, our product is a 10. And a 2 and a 6, our product is a 12. Next one, we roll a 3 and a 1, our product is 3. 3 times 1 is 3. 3 and a 2, our product is 6. We roll a 3, and then the second dice a 3, our product is 9. We roll a 3 on one dice and a 4 on the other, our product of the two dice is 12. A 3 and a 5, our product is 15. A 3 and a 6, and our product is 18. Now we got a 4 and a 1. It's not going to be a 3. Let's get rid of that. A 4 and a 1 is a 4, of course. 4 times a 2 is going to give us an 8. 4 times a 3 is going to give us a 12. 4 times 4 is going to give us 16. A 4 times a 5 is going to give us 20. 4 times 6 is 24. Next roll 5 and a 1, we get a 5. 5 and a 2, we get a 10. 5 and a 3, we get a 15. 5 and a 4, we get a 20. 5 and a 5 is a 25. 5 and a 6 is a 30. And now down here we get a 6, 6 and a 1. That multiplies together to give me 6. 6 and a 2 multiplies together to give me 12. 6 and a 3 multiplies to give me 18. 6 and 4 is 24. 6 and 5 is 30. And 6 and 6 is 36. So if you count up all these different possibilities of a row, 1, 2, 3, 4, 5, 6. There's 6 rows of 6, that's 36. Again, 6 events here, 6 possible events here, so together, and we multiply them to get 36. 36 is our bottom number. That's the total possible outcomes. So 36 is our bottom number for both of them. Now, it might reduce if we want to reduce it, but we don't have to. The reason probability doesn't always make you reduce is because it is accurate to say there's 36 different options. So sometimes we don't really want to reduce it because we want to know how many different options that's out of. Now, how many of these options are odd? So in other words, what's the probability of odd? Well, we've got 1, 3, 5. So far, it looks like 50-50. But then notice when this die is a 2, not one of these is odd. They're all even. Then when it's a 3, well, we've got 3 is an odd number. 6 is an odd number. 15 is an odd number. We only have 3 odd numbers. If this dice is a 4, none of these ends up being odd. If this dice is a 5, we have every other one is odd. Once again. And then, if the dice is 6, they're all even again. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Only 9 of the 36 times will be odd, which is to say 1/4 of the time will be odd. But notice all the rest are evens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27 times. 27 times. It could be even, which is to say 3/4 of the time. Because 9 goes into 27 3 times, 9 goes into 36 4 times. 3/4 of the times it'll be even. So if you are the player who gets points for the even, you will probably win. Now, just to kind of point this out, if I add these two fractions together, I get 36 over 36 or 1. Same if I do it in the reduced form. So remember, they add up to 1. The other thing I want to point out is the probability of even is the same as saying the probability of not odd. So not necessarily in this case, but oftentimes it's very hard to find the probability of an event, and that sometimes it's easier to find the opposite, the probability of it not happening, of its opposite not happening. So the probability of odd plus the probability of not odd also would equal 1. All right, now this is just a question I have for you. If I were to randomly pick a marble out of here, let's say I did it a couple times there randomly, I got blue. Right? Again, randomly I get red. And I am actually closing my eyes before I do that. Randomly I get blue again. So 3 times. Out of those I got 2/3. 2 out of the 3 were red. Was that theoretical or empirical? Is that theoretical probability or empirical when I just drew out the marbles? Okay, that was an example of empirical. I actually had to do some sort of experiment or observation. Now, if instead I said, okay, there's 4 blue marbles and there's 9 marbles altogether, so my probability of getting a blue would be 4 out of 9. That would be an experiment, a theoretical probability. Theoretical. And it's based on theory. There was no actual experiment. So keep those straight. And you should be able to do all the homework on your syllabus listed beside the following topics: theoretical and empirical probability, and or probability, and tree diagrams. The only one we haven't done is conditional probability. And that concludes this lesson.
This is issue 44.